In this video, we will see uh, in short all the properties of White's and stationary random process. Detailed description of all this we have already covered in the previous videos. So, for White's and stationary random process, mean that is E of xt is constant. Mean is constant. That E of xt has the notation mu x also. So, mean is constant. That means we can write it as E of xt1 is equal to E of xt2 is equal to E of xtk is equal to mu x, because it is not depending on the time. So for all the instances where you observe the random process, that means at t1 t2 up to tk, the mean is constant. So when you observe the random process at a particular instant, you will get the random variable. So we can say that mean of a random process of stationary random process, so mean of a random process that is stationary is equal to mean of a random variable. So how we can say this? Because it is not depending on the time. So at whatever the random variables you obtain by observing it at different time instance is the same as the random process. So so many times you have to use this expression. That means instead of t1 t2 you are writing it as xt, and second instant is x of t plus tau. So mean is constant for stationary random process. Mean is nothing but the, if you make the square of this mean, then you will get the dc power. So here the correction is that you have to make it as mu x square, then you will get the dc power. So dc power is constant, it is not depending on the what time. So let us find the mean square value. So mean square value is E x square t. It is nothing but the total power of that process. So E x square t for the stationary random process is r x x 0, that is constant. That means it is not depending on the time. So E of x square t1 is equal to E of x square t2 is equal to E of x square tk. So that is equal to r x x 0. Again, instead of t1 t2 you write one instant as t and another instant as t plus tau. So E of x square t is equal to E of x square t plus tau is equal to rx 0. Here also we can say that total power of the random process is equal to total power of the random variable, that is equal to rxx 0. Next, let us see what about the AC power or variance. We know, so always keep this expression in mind, that E of x square t is equal to sigma xt square plus mu xt square. That means total power is equal to AC power plus DC power. So we have seen for the stationary random process that this DC is constant, this is also constant, it is not dependent on the time. So let us see what about the, if now sigma x square t is AC power, so that is equal to E x square t minus mu x square t. E x square t is r x x 0 and mu x square t is mu x square only, because it is not dependent on the time. So here also we can say that AC power is constant. So 3 points we got till now, that for the stationary random process AC power, that is variance, is sigma x square. That means it is not depending on the time. I am not writing sigma x square t. DC power is mu x square. It is not dependent on the time, it is also constant. And total power E of x square t, it is equal to r x x 0. So it is also not equal to, it is also not dependent on the time t. So this is very important, that total power of the stationary random process is rxx 0, that is autocorrelation function at 0th value, 0th instant. AC power is sigma x square, that is constant. DC is also constant. Next, let us see what about the autocorrelation function. Autocorrelation function is given by ext x of t plus tau, expectation of xt x of t plus tau, and written as xx is written here. And autocorrelation function is dependent on t plus tau minus t. That means it is dependent on the difference. So here tau is there. So autocorrelation function is dependent on the difference only. So what about the autocovariance function? So autocovariance function Cxx tau is equal to Rxx tau minus mu x mu y, because means are also constant here for the stationary random process. So this shows that the covariance function is also dependent on tau only, that is time difference. It is constant. So mu x mu y are constant. So autocovariance is also dependent on time t. Now let us see cross correlation. Cross correlation means the formula is E of xt y of t plus tau. So x you have to write here and y here, and difference is tau. So cross correlation is also dependent on time difference of the instances. Cross covariance is nothing but cross correlation minus product of the means. So Cxy tau is equal to Rxy tau minus mu x mu y. I have already written here tau because we are just enlisting the properties of the White-Stein stationary random process. Why tau? Because cross covariance is also dependent on the difference between the time instances. It is not dependent on the individual time instances. Cxy2 actually Cxy or covariance, we can write it as covariance is of xt comma y of t plus tau. So instead of that I have directly written Cxy of tau because this is the property enlisting video. That's why we are saying that, or I have written it as directly tau instead of xt and y of t plus, instead of writing xt and y of t plus tau. So what we have studied that for the White-Stein stationary random process, mean is constant, so we are writing it as only mu x. Variance is constant, so we are writing it as sigma x square. Mean square is a DC power which is also constant. Sigma x square is AC power which is constant. Total power is E of x square t. It is Rxx of 0. Then autocorrelation is dependent on tau, that is time difference. Cross correlation dependent on time difference. Cross autocovariance dependent on time difference. Cross covariance dependent on time difference. So these are the properties of the stationary random process or White-Stein stationary random processes.